Next up in our discussion of quantified statements is generalization. So instantiation was a technique that allowed us to go from a bound variable statement to a free variable statement, a quantifier, and we got rid of it. Is there a corresponding process that reverses that? If we have a statement with free variables, can we introduce quantifiers into it in an allowable way in order to bind them? Yes, there is such a process, and it's called generalization. Unsurprisingly, it works differently depending on whether you're trying to introduce an existential or a universal quantifier. Now, instantiation was very straightforward when it was universal. If a statement is always true, then it was true for any choice of term we wanted. But existential generalization was restricted. So when a statement was always true, easy. But if it's only sometimes true, there were careful things we had to do. We could only introduce variables that did not exist as free variables anywhere. This balancing act of one of them is very easy to do and one of them is very restricted is reversed for generalization. Introducing an existential quantifier is easier. It's easier to say a statement is sometimes true. It's harder to introduce a universal quantifier. It is harder to say a statement is always true. Since existential generalization is the more straightforward of the two, we'll begin with that. So here's how the rule works. If p of x is any statement you want that has the free variable x, you can turn it into an existentially quantified statement, there exists y, p of y, where y is any variable at all that you want to use. This is called existential generalization, and we abbreviate it this way: existential generalization where x was replaced with y. Because p of x was true, assuming that this was a legitimate thing, it follows there must be some choice of variable so that p of y is true. Specifically, you could have chosen x. So since p of x is true, it is true that there exists a choice of y so that p of y is true. And it doesn't actually matter if this variable exists anywhere else as a free variable. There exists a y so that p of y is true just means there is some choice of variable for which p of y will be true, and we already know that x happens to be a particular choice. So since existential instantiation is restrictive, okay, you shouldn't expect that this easy way of existentially generalizing is going to be terribly helpful to you. It's easy to introduce this existential quantifier, but it's very difficult to get rid of it again. So this is not going to be something that you can use to prove tons and tons of stuff for free. Let's take a look at an incorrect proof. Suppose p of a is a true statement, and there does exist a choice of x so that q of x is true. You shouldn't be able to derive that there is a choice of y so that both are true simultaneously. You know that p of a is true. You know that for something, q of x is true. You have no way of knowing if it's the same thing. So that you shouldn't be able to conclude that there is a choice for which they're both true. So let's see what mistake is made. So look at the following and try to see if you can spot the mistake. Line 3 is a problem. Okay, so the first two lines are just givens. That's what it is. Existential instantiation, line 2. Is this existentially quantified? Yes. Replace every x with an a? Okay. But are you allowed to do that? No. The variable a exists as a free variable in line 1. So you can't use it in your existential instantiation. Everything else, by the way, is fine. If p of a and q of a both existed, then I could conjoin them, and then this existential generalization is okay. The only flaw here is in this existential instantiation. And again, the reasoning is p of a is true, and there is some choice for which q of x is true, but you shouldn't be able to assume that it's the same one. For example, if p and q referred to even versus odd numbers, 7 is an odd number, and there does exist an even number, but it isn't possible to find something for which both is true. All right, existential generalization is pretty straightforward, but universal generalization is going to have some restrictions. Okay. If you have a statement P of A happens to be true, can you possibly derive that for any choice of x, P of x is true? This is abbreviated as universal generalization, where the free variable A was replaced with the bound variable x, and it's allowable under the following conditions. A is not a constant, it's actually a variable. It never occurs free in any of your givens, and it was never used in any existential instantiations. So the variable that you are trying to generalize, so from this free variable that's not a specific constant, it's actually a variable, you're trying to generalize it. It was never a free variable in any of your givens, and you never used it in existential instantiation. Okay, so if you want to go from a specific to a general, it must not have been important somehow as either a specific constant from the domain of discourse, and the only way it ever showed up into the proof was via universal instantiation. So if it was never in a given, then how did it show up? The only way it showed up was either an instantiation of the existential or universal varieties, but I'm forbidding existential instantiation. So it's not a specific constant, it didn't start off in the proof in a given, and it didn't show up via existential instantiation, so the only way it ever showed up as a free variable was via universal instantiation. Then you can universally generalize it. Okay. The only way it ever showed up as a free variable was from a universal instantiation, which means it wasn't anything specific. It could have been anything. So let's take a look at another incorrect proof. Now, as a statement, as a rule of inference, this is transparently absurd. There is a choice for which a statement is true, therefore it's always true. That doesn't make any sense at all. Okay? For example, P of x could be even numbers. Is there an even number? Sure. Therefore, all numbers are even. No, that is bad reasoning, and let's see an error that students could make where they might think this is true. So what's the error in this proof? It's only in line 3. The given is the given. I then existentially instantiate with a whole new variable, that's fine. Can I universally generalize replacing all of my a's with x's? Okay. The free variable a that we are attempting to replace was not the result of universal instantiation, but rather existential instantiation. There's a special choice for a for which this is true, therefore always? No. When you are replacing a variable in universal generalization, the variable you're replacing cannot have appeared in any given as a free variable and cannot have appeared via any existential instantiation, which it did here. Okay, this is really the core reason why this restriction exists. If a variable was introduced by existential instantiation, it's special and not general. But now that we have these rules in our tool belt, proper use of both instantiation and generalization, as long as we're correct about it, we can prove a lot of stuff. So we're going to go over a rule of inference known as universal modus ponens. It's very similar to our old modus ponens. Once we derive it, it's going to be a rule of inference that we can refer to. Here it is. For any x, P of x implies Q of x. P of c happens to be true, therefore Q of c is true. And here's the proof, and we'll take a look at it line by line. Well, we start off by declaring the givens. There they are. No controversy there. Line 3 says, universally instantiate line 1. Yes, line 1 is a universally quantified statement. Replace all the x's with c's. So drop the quantifier and replace all the x's with c's, and this is what you get. Now, did we make a legal choice of variable to plug in? We did, because universal instantiation is totally open in that regard. You can use any variable or term you want here. So this is fine. Next, modus ponens, line 2 and 3. I have a conditional statement and I have its hypothesis. I extract its conclusion. There it is. Done. Okay, notice that this universal instantiation is allowed to use any variable even if it already exists. And in this case, the variable c already existed, but universal instantiation is fine with that. You could not do this if it was an existential instantiation. If this here was there exists in X, you couldn't use the variable c because existential instantiation is much more restrictive, and there is no corresponding rule called existential modus ponens. It doesn't work. Just because there is a choice of X for which P of X implies Q of X doesn't mean that C happens to be one of the ones that makes this work. Sometimes P of X implies Q of X. Is this one of them? I don't know. That's why existential modus ponens doesn't work. In this version, P of X always implies Q of X. P of C happens to be true, therefore Q of C is true. So let's do an example of a two-column proof of this rule of inference. Notice that the given is for all x, P of X implies Q of X, and the claimed conclusion is for all x Px implies for all x Q of X. This looks like we're simply distributing the quantifier across the arrow. And in terms of mechanical manipulation of symbols, I guess that's true, but we've really changed things. Up in the given, the conditional arrow has hypothesis, P of X, and conclusion, Q of X. This is now a predicate statement that isn't really a statement until you make a choice of X, but then we bind the variable. Down here, however, the hypothesis is for all x P of X, and the conclusion is for all x Q of X. Line 1, we state the given. Line 2, we're going to assert our desired conclusion. Since we did assert a conditional statement, we're going to go ahead and do a direct proof and assume its hypothesis. And as we mentioned, the hypothesis of this conditional statement is for all x P of X. Next up, we universally instantiate line 2.1, replacing all x's with a's. It is universally quantified. Universal instantiation does not put any restrictions, so no big deal. Strike out the quantifier, replace x with a, there we have it. Next up, universal modus ponens between lines 1 and 2.2. Universal quantified conditional statement, hypothesis for one specific choice, therefore conclusion for the same choice. That's the rule of inference we just proved of universal modus ponens. It's always true that P of X implies Q of X, so since P of A is true, Q of A must be true. And finally, universal generalization of line 2.3, replace all your A's with X's. Now we have to be careful. Universal generalization is one that's tricky. I'm taking a statement and I'm replacing the free variable with X. This variable that we're replacing cannot have ever appeared in a given and cannot have ever been introduced by existential instantiation. It didn't appear in the only given. And while it was introduced by instantiation, it was introduced by universal instantiation. So A is an allowable thing to be universally generalized. It wasn't in a given and it only showed up from universal instantiation. So I can generalize it, replacing it with anything I want. So I can replace it with X. I didn't have to replace it with X, but there was a very good reason why I wanted exactly this to show up for all x Q of X. Because we've now completed the direct proof of our assumption, of our assertion. We assumed the hypothesis and we derived the conclusion, which completes the direct proof and therefore the entire proof of this rule of inference. Sometimes statements have multiple quantifiers in them. Okay, and the order of quantifiers can really matter. We've already seen that. If the domain of discourse, for example, is people watching the video, you can have a statement, person X loves person Y. In which case, for all X, there exists a Y, so that P of XY means for any person X, there is a person Y, so that X loves Y. But if I switch the two quantifiers, there exists a Y, so that for any X, P of XY means there is a person, so that everyone else loves them. But when two of the same quantifier appear in succession, the order actually does not matter. So let's continue our discussion of multiple quantifiers. There are two rules of inference here, and what they say is if I have two universal quantifiers, I can actually switch the order. If I have two existential quantifiers, I can switch the order. So multiple quantifiers, the order matters unless they're the exact same quantifier, and then it doesn't really matter what order you put them in. Here are the corresponding proofs. Let's take a look at them one by one. State the given, universal instantiation, which is totally free, I can do anything I want. Universal instantiation, which is totally free, I can do anything I want. Now I universally generalize. The free variable a only showed up based on universal instantiation, and then the same thing here. Basically, we instantiate x, we instantiate y, and then we generalize them in the opposite order, and the effect is to have switched the two universal quantifiers. Looking over here at existential, okay, existential instantiation is restricted, but a is an entirely new variable, so I stick it in. And b is an entirely new variable, so I stick it in. And now existential generalization, I can do whatever I want. But again, we instantiate them in one order and then we generalize them in the other. And again, the instantiation is easy for universal, but generalization is hard. The instantiation is hard for existential, but the generalization is easy. Okay, so in that second proof, we've sort of reversed which steps we had to be careful about, but in both of them it does work out. So continuing our discussion of multiply quantified statements. We can write two quantifiers of the same type in any order, so what's typical is to abbreviate that. Instead of writing for all x for all y, since it doesn't matter what order we put them in, we just go ahead and say for all x and y, p of xy. And then if you want to instantiate one of these doubly quantified things, it doesn't really matter which one's on the outside, so instantiate either one that you want. So for example, since these are both universally quantified, I can instantiate one and then the other, but it doesn't matter what order I do it in. So you can just say, replace all of your x's with a's and y's with b's. What this does is it does two consecutive applications of universal instantiation at once, because it didn't really matter what order you did them in. If you're doing multiple substitutions on multiple variables, use commas to separate them. But you do have to be very careful, okay? You cannot doubly instantiate this existential by replacing x with a and y with a. Because existential instantiation is so restricted, once you instantiate one of them with a now exists as a free variable and you can't instantiate it again using a. You can, however, obtain something like p of ab if you instantiate the first with a and then the second with b. Well, since they both are variables that don't occur anywhere else, presumably, that's okay. So now let's take a look at another possible two-column proof of a rule of inference. For all x, p of x implies, for all y, g of xy. For all a and b, g of ab implies e of ab. There is a c so that p of c, therefore there is an m and n so that e of mn. What do these things mean? I don't know, nothing. It doesn't really matter. Okay, while later on we're going to want to work with things that carry meaning, I think it's helpful to begin this by just focusing on the form of how things are proved without getting caught up in what they are supposed to represent. But let's go ahead and take a look at a proof. We start off by declaring the givens, just as we always do. Now there are a few things we could do, but what I'm going to do is existential instantiation of line 3, replacing the bound variable c with the free variable t. It is existentially quantified. Existential instantiation, however, does have restrictions. The free variable I put in better not exist anywhere else as a free variable, and t does not. It's nowhere to be seen. So this is okay. Next, universal instantiation of line 1, where I replace all of my bound variable x's with free variable t. Okay, this is a universally quantified statement, so drop the quantifier, replace x's with t's, and universal instantiation is very open. There's no restriction on what you put in, so this is fine. I replaced this x and this one with t's. You have to replace every instance of the variable. Now observe that between lines 4 and 5, I can just apply modus ponens. P of t implies this, and I do have P of t, so I must have the conclusion. Universal instantiation of line 6. Replacing my bound variable y with my free variable r. It is universally quantified, and universal instantiation has no restrictions, so I just replace my y's with r's and call it a day. Now I can apply universal modus ponens. Look at line 2. No matter what choice of variables a and b, g of ab implies e of ab, and I do have g of t comma r. So I must have e of t comma r. That's universal modus ponens. And now, existential generalization on line 8, replacing t's with m's and r's with n's. Existential generalization has no real restrictions on it. So I can just go through here, replace t with m, r with m, and quantify them existentially. And that's our desired conclusion. But lines 4 and 5 cannot occur in the opposite order. Notice that this only refers to line 3 and this refers only to line 1, and they don't refer to each other, so why does it matter what order I do it in? If you did this line first, you're universally instantiating, which is totally cool. Then you'd say, existentially instantiate by bringing in the variable t, but the variable t would already exist in this line, which came first. So in general, you want to make sure that any existential instantiations are done first, because existential instantiations have restrictions and universal ones don't. So do the things that have restrictions before you do the ones that don't have restrictions. Anytime you're instantiating, existential should be done first. It's not a hard and fast rule, it's just a nice rule of thumb. For generalizations, it's the other way. Since universal generalizations have much more restrictions on them, if you're going to be doing any of them, try to get them done quickly. Existential generalizations, however, have no restrictions and can be pushed off to the end.